Okay, let's dive right into this explainer. Today, we're uncovering how Uber built a massive, automated detective to make sure their real-time data is absolutely flawless. I mean, we are talking unprecedented scale here. We're going to explore exactly how their data engineering team achieved this level of operational excellence. Specifically, how they lock down critical data movement with some pretty brilliant reconciliation tests and data quality checks. But to set the stage, I want to start by asking a question that affects almost everyone who's ever opened the app. Have you ever wondered how Uber actually calculates surge pricing when you're just trying to get a ride home after a massive concert? Well, the answer relies entirely on an invisible, massive flow of real-time data. It's not magic, It's all math and data pipelines. At its core, those surge multipliers are determined by real-time machine learning models, and they're constantly balancing two giant data sets: supply data, which is just the number of drivers available in a specific area, versus demand data, so the rider's actively opening the app to request a trip. If supply is higher than demand, the surge drops down to its minimum. But here's the catch. Any system glitch that drops or delays that supply data instantly corrupts the surge value. Which brings us to Section 1, the surge pricing problem, when bad data strikes. The stakes here are incredibly high, because if bad data silently corrupts the marketplace, the machine learning models don't just crash. Nope, they silently degrade. They start making bad decisions. And that instantly leads to inaccurate pricing, less efficiency, and actual lost earnings for drivers. Relying on humans to manually investigate these silent degradations? Completely impossible at Uber's scale. They're handling tens of thousands of datasets. So this absolutely critical business need is what led them to build a consolidated data quality platform, known internally as UDQ. Moving right along to Section 2, defining true data quality. To build an automated detective, Uber first had to standardize exactly what a healthy dataset actually looks like. Because, well, before you can catch bad data, you really have to know what good data is. What's fascinating is they took years of past incident reports and boiled them all down into 4 core pillars. They look at freshness, completeness, duplicates, and cross-data center consistency. By categorizing all their incidents into these standard pillars, they were able to systematically cover every single quality aspect of a dataset. Let's zoom in on one of these pillars for a second. Freshness isn't just some vague feeling of, hey, is this data new? Uber defined it strictly as the exact delay after which a dataset is guaranteed to be 99.9% complete. Defining freshness mathematically like this is super smart because it lets the system establish an exact SLA, or service level agreement threshold. Basically, it draws a definitive line in the sand before a dataset is cleared to be used by those crucial downstream machine learning models. The simplest form of this validation uses really straightforward SQL queries acting as mocked assertions. For example, the system simply asserts that daily supply counts haven't inexplicably flatlined below 10,000, or that the weekly consistency hasn't just dropped off a cliff. It's an incredibly effective, lightning-fast baseline test to run. Let's look at Section 3, automating the quality tests. Now, manually writing SQL tests for over 2,000 top-tier critical datasets would take an engineering team forever. So Uber automated the entire generation process in 3 really clever steps. First, they fetch metadata, like those SLAs and partition keys. Second, they auto-generate test definitions, not just for one table, but for its entire upstream and downstream lineage. And third, they run daily Apache Spark jobs to actively prune obsolete tables out of the system. By pulling this metadata and analyzing the lineage, their test generator automatically creates 100% test coverage, and it adapts dynamically as the data pipelines naturally change over time. It's pretty amazing. All those generated tests then feed into a Celery-based web service called the Test Execution Engine, which handles a staggering 100,000 daily executions. The underlying technology making this possible is absolutely fascinating. The engine uses abstract syntax trees, or ASTs. Instead of hard-coding thousands of specific tests, parsing them into an AST is basically like translating math into a universal language the machine understands perfectly. This allows the engine to interpret a virtually limitless variety of mathematical test assertions with incredible efficiency. All right, on to Section 4, testing critical data movement. Making sure massive datasets perfectly match across entirely different data centers is, frankly, a notoriously difficult problem. Uber engineered a brilliant trade-off here to ensure cross-data center consistency. They actually use two types of reconciliation tests. First is a lightweight test. This is super fast and merely compares the total row counts between data center A and data center B. But they pair that with a Bloom filter test. This one is slower, but it compares exact content to provide really deep diagnostics. If you aren't familiar with it, a Bloom filter is a probabilistic data structure used to perform high-speed membership checks from a massive set. Think of the Bloom filter almost like a highly efficient digital bouncer. It takes the VIP list, the data records from data center A, copies that filter over, and checks it at data center B. If there's a discrepancy, the Bloom filter can identify the precise row of missing data. That gives engineers the exact needle in the data haystack they need to fix the issue fast. Next up, Section 5, Taming the Alert Fatigue. Look, if your system is running 100,000 tests a day, you absolutely have to prevent your engineering team from getting buried in false positive alerts. Uber's solution? Something called the sustain period. Let's say at 1 a.m., a transient pipeline lag fails a test. If you page an engineer at 1 a.m. for a 1-minute lag, well, they're going to learn to hate the system pretty fast. Instead, the system triggers a sustain period of, say, 4 hours. It marks the data as a warning, but just waits. Only if the failure persists beyond that acceptable time frame, at 5:01 a.m., does the test status actually change to fail and send out an alert. They also solved alert fatigue by grouping alerts hierarchically. Think about it. If data arrives late, it's obviously going to fail the downstream completeness test too, right? So the system is designed so that if a data set fails its freshness check, it automatically suppresses the subsequent completeness alerts. This ensures developers aren't getting spammed with 3 different tickets that all point back to the exact same root cause of data latency. And for the alerts that do successfully go through, well, they built an automated incident manager. Once a valid alert is triggered, the system doesn't just sit there. It waits and performs an exponential back-off rerun of the test. The crucial point here is this. If the data pipeline naturally catches up and the test eventually passes, the system completely auto-resolves the ticket. Literally, no human engineer ever has to manually close it out. Talk about a massive operational win. Which brings us to our final section, Section 6, the verdict on automated quality. We've seen the architecture, but how well does it actually perform in the real world? Well, by combining abstract syntax trees, cross-data center Bloom filters for reconciliation, and smart alert suppression, Uber turned a pretty chaotic data problem into a highly tuned machine. The ultimate proof of success is that 90% hit rate right there. The platform successfully auto-detects roughly 90% of all data quality incidents before they ever impact downstream operations or business metrics. As we wrap up this explainer, I want to leave you with this provocative thought, especially for those of you working with complex data. If bad data is the silent killer of machine learning, how is your team currently interrogating your pipelines? Are you systematically running data quality checks and testing your critical data movement? Or are you just kind of hoping it all works out? Think about how you can apply these automated detective principles to your own workflows. Keep learning, and I'll catch you in the next explainer.